Now let's talk about law of gravitation. A law of gravitation is also known as Newton's law of universal gravitation. And this law, in this law, Newton proposed that every object in the universe attracts every other object with a force, and this force depends on two things: the masses of the object and the distance between them. And mathematically, it's given as the force is equals to a capital G times m1 m2 over d square. Here m1 and m2 are the masses, d is the distance between their centers, and g is the universal gravitational constant, which has a value of 6.67 into 10 to the minus 11 Newton meter square per kg square. One thing we need to remember is that when we say the distance, we are mainly focused on distance between the center of two objects, not the starting point. Rather, we are interested in the distance between the centers. And we should also remember that the gravitational force is always attractive. We can see here we have a mass 1, mass m here, and mass capital M here, and we can see a force of m going toward m is exerted by object m, and this force is attracting this small mass m toward its center. And similarly, this small mass m has an attractive force toward its center, attracting the mass capital M. So the gravitational force is always attractive, and the distance we are interested in is the distance between the center of two objects. And another key point is that gravity follows an inverse squared law. That means as the distance, and we from the previous equation we saw that fg is equals to g m1 m2 over d square, and if we consider d as a constant, we can write it as gravitational force is inversely proportional to the square of the distance between them. And this means as the distance doubles, the force between two objects is 4 times weaker. This is why gravity feels strong when we stand on, for example, Earth's surface, but is very weak when we are far away in the space. And since it's inversely proportional, we should also understand that the force will decrease as the distance between the objects is increased. D gets larger, gravitational force gets smaller. And here's a conceptual question we can look at. There are three equal masses. Three equal masses are located as shown. What is the distance of the total? What is the direction of the total force acting on M2? And the options are to the left, to the right. The forces cancel. The forces cancel such that the total force is 0. It is impossible to determine from the figure, and we can use this relation where we said that the force is inversely proportional to the squared of the distance. Now if we look at here, m1 and m2 has a shorter distance compared to m2 and m3, or m1 and m3, right? So the strongest force is the attractive force between m1 and m2, and the attractive force between m2 and m3 is relatively smaller, and the attractive force between m1 and m3 is even smaller. So we can say that the the direction of the total force acting on m2 will be to the left, because the shorter the distance, the higher the uh, force is. So the force going this direction is comparatively small than force going this direction. And if we say this is f1, this is f2, and the net force on m2 is f net is equals to f2 minus f1, and we can see f2 is bigger, so it's going in the direction of f2 force. Now let's look at a numerical example. It's asking what is the gravitational force between two people each of mass 100 kilograms standing 1 meter apart. Suppose we have two people each with 100 mass standing at 1 meter, and the force between in order to calculate the force between them, we can use the Newton's universal law of gravitation, and use this formula where m1 is m equal to m2 is equals to 100 kilogram. And if we substitute these numbers back to the formula, and we get where constant g is 6.67 10 to the minus 11 Newton meter square per kilogram square. So if we substitute these numbers, 6.67 into 10 to the minus 11 Newton meter square per kg square times m1 is 100 kilogram, m2 is 100 kilogram, and the distance between them is 1 meter square. So we get an answer of 6.67 into 10 to the minus 7 newtons. And if you look at this number, that's less than a millionth of the weight of an say an apple. So we can say for everyday objects, gravity between them is very small and negligible. But when the masses are huge, like planets or moons, that same law of universal gravitation explains the orbits and tides we see. So in summary, we can say the gravitational force between human sized objects are really small, so we do not feel the forces, the attractive forces between each other. But if we are looking at a very large object, we can feel the gravitation. For example, the gravitational pull by Earth's surface. If you throw something in the air, it will come down because of the gravitational pull exerted on the object by Earth's mass. Now we have the next question. What is the force of gravity of a person whose mass is the question is asking force of gravity of a person whose mass is 82 kilograms and is standing on the surface of Earth. So we have unknowingly we have been calculating this force from our previous sections, and we were using it as the weight of the of an object. So the weight of an object is basically the force of gravity experienced by the object. And we can see here for the weight of an object is mass times acceleration due to gravity, and the mass is 82 kilograms. 82 times g is 10 meter per second square. For simplicity, if you want to calculate precisely, you can use 9.8 meter per second. And now we will get the total force of gravity is around 820 Newton. The same problem we can also solve using the Newton's universal law of gravitation if we know the mass of Earth as well as the mass of the object we are looking at, in this case the person's mass. And let's look at the calculation. Here I have provided the mass of Earth, which is 6 into 10 to the 24 kilograms, and also the radius of the Earth. So the distance is the distance between the center of two objects, right? But if you look at here, the Earth, the size of the Earth is very large compared to a person, so we can just consider this person as a point object, and we can just use the radius of this Earth as our distance between two objects. Since the size of the object compared to Earth's radius is negligible. Now if we substitute these numbers, the constant g is 6.67 into 10 to the minus 11 Newton meter square per kilogram squared, and m1 is the mass of Earth, 6 into 10 to the 24 kilograms. M2 is the mass of the person, which is 82 kilograms, over the radius of the Earth, 6.37 into 10 to the 6 and square. And if we simplify these numbers and calculate the final numbers, you will get approximately 820 Newton. So we can either use this formula or this formula. If we know masses and radius, we will get the same number. And one thing you need to remember is that if you are using this formula, this includes mass times acceleration due to gravity, and this, however, it depends on the mass of the bigger object. For example, in this case, the mass of Earth. And if you look at other planet or moons, for example, the gravity will be different, and you have to use the appropriate acceleration due to gravity if you are calculating on different planets. Now we just calculated the force of gravity, and now let's look at where we get this acceleration due to gravity we have been using, where we said it g is equals to 9.8 meter per second square on Earth's surface. Now so far we have shown that the force, the attractive force between two masses is given by this universal law of gravitation. F is equals to g m1 m2 over d square. And if we look at this m1 and m2, these are masses, right? And if we are looking at the acceleration due to gravity of Earth, we can say the one of the mass m1 is equals to mass of Earth and another mass m2 is mass of an object, we are interested in calculating the acceleration due to gravity, and the mass of Earth is 6 into 10 to the 24 kilogram, and the distance between the object and the Earth's core is basically the radius of Earth, and which is 6.37 into 10 to the 6 meter. Now if we substitute these numbers back in this equation, we can rewrite it as so F is equals to G m1 m2 over d square, and if we take this two portion out, where this is a fixed number, because this is the mass of Earth, which is a fixed number, we know, and this d square is, this d is radius, which is also a fixed number, we can say, and we also know that g is also constant. So if we isolate these numbers, overall we will get a constant number. So we can simplify this as some constant number times mass of an object. And if you calculate this using all these numbers of g, m and d square, you will get approximately 9.8 meter per second square. There are a few more numbers after 8, but we will just approximate it to 9.8 meter per second square. This is where we get our acceleration due to gravity. And if you change this mass, capital M mass, for example, to a mass of moon, then you will get gravitational acceleration due to gravity at moon surface. To summarize, Newton's law of gravitation is universal. It applies to, for example, apples falling from trees, people standing on Earth, and as well as planets orbiting the sun, moons orbiting the planet, and it explains both the everyday experience of weight and the grand motion of celestial bodies.